Welcome to Sri Jayendra Ink Zone. Good morning, all of you. Today we are discussing. So in the first lecture we have done already ionic bond and compounds of ionic bond. Second lecture we have done covalent compounds and covalent bond. Next we are going to do new topic in this chapter, that is bond parameters. So in this lecture we are going to discuss bond parameters. So this bond parameters is very important. Very important, these bond parameters. So what are bond parameters? The covalent bond is characterized by the following bond parameters. As I already told you, covalent bond is having directional, so it has bond parameters. So the measurable properties of all the measurable properties of all of the bonds present in the molecule is called bond parameters. So what are the measurable properties? We have bond length. First one we have bond length. Next bond angle. Next bond order. Next bond enthalpy. So bond energy or bond enthalpy, and how they are related to with each other. That also we'll discuss. So this is very important for objective point of view, and they'll ask about bond length and bond order, the decreasing order and increasing order. So these points are very important. Now let us see what is bond length. It is defined as the equilibrium distance between the nuclei of two covalently bonded atoms in a molecule. Bond lengths are determined by means of spectroscopic studies or X-ray diffraction studies only. As they are very small in nature, we measure them in picometers or angstroms. Picometer means 10 to the power of minus 12, and angstrom means 10 to the power of minus 10 meters. So in covalent molecules, the sum of covalent radius of two bonded atoms is equal to bond length. So the sum of covalent radius of two bonded atoms is equal to bond length. This is called the definition of bond length. The covalent radius is half the distance between the two atoms. How to calculate covalent radius? As we discussed in periodic configuration, periodic classification. So the covalent radius is half the distance between the two atoms of same element bonded by a single covalent bond. So bond lengths are some of the bonds given below. Bond lengths of some of the bonds are given below. So what are the bond lengths we have? C single bond H 107 picometers. These are all observed in spectroscopy, that is X-ray studies only. And C single bond C 154. This is alkane. C double bond C alkenes. And C triple bond C alkynes 120 picometers. So what do you understand by these three? C single bond C 154, C double bond C 133, and C triple bond C 120. So as the number of bonds increases, bond length decreases. So as I told, I'm writing here the statement, as the number of bonds increases, the bond length decreases. So as the number of bond increases between similar atoms, between two atoms, the bond length decreases. So this statement is very important. So if you can see here, C single bond C, this is alkanes, this is alkenes, and this is alkynes. So 154 picometers, 133 picometers, 120 picometers. So this is between similar carbon and carbon, 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 carbon. I'm telling about alkanes, alkenes, and alkynes. So if you take CH bonds, 107 picometers, OH bonds, 96 picometers, NO bond, 136 picometers, CO bond. These values are not, means we should not, no need to remember this. Just they have given examples. So what is bond length? Sum of the distance between the two nuclei. So covalent radius. Sum of the covalent radius of two combined atoms is nothing but its bond length. And bond length is nothing but parameter of bond. So I hope it is clear. As the number of bonds increase between two similar atoms, the bond length decreases. Next. So if there is back bonding, so back bonding you will find in certain molecules like boron, diboron, B2H6. B2H6 we have back bonding. So what is B2H6? We'll study that B2H6. So back bonding means B2H6 example. So B2H6 is called diboron where we have back bonding. So in back bonding molecules, bond strength increases and thereby bond length decreases. So not only in back bonding in molecules, bond strength increases. If the bond strength means bond enthalpy increases, bond length decreases. So bond enthalpy is proportional to 1 by bond length. So as the bond length increases, bond enthalpy decreases. I hope it is clear. So what is bond enthalpy also we'll discuss now. So first, what is bond length? It is clear now. So as the number of bonds between the two combining similar atoms are increasing, the bond length decreases. So that we can observe in the case of C single bond C 154 picometers, C double bond C 133 picometers, and C triple bond C 120 picometers. Next, covalent bonds are directional in three-dimensional space. The bond angle is defined as the angle between the covalent bonds having the central atom in a molecule. So covalent bonds are directional, as I already told you. The bond angle is defined as the angle between the covalent bonds around the central atom in a molecular ion. So bond angle is expressed in degrees and it can be measured by spectroscopic studies again. So the bond angle data help us to know the shape of the molecule. So the bond angle helps us to know the shape of the molecule. For example, if the bond angle is 109 degrees, for example, if the bond angle is 109 degrees, it is tetrahedral shape. It will take the shape of tetrahedral. This we will observe in case of methane. So if the bond angle is 180 degrees, it is linear, straight line. So linear shape like this. So with the bond angles, we'll be knowing the shapes of the molecules. I hope it is clear. So what is bond angle? Angle between the covalent bonds around the central atom in a molecular ion. So example, in case of water, the bond angle is 104.5 degrees. 104.5 degrees. In water molecule, the bond angle between two OH bonds is 104.5 degrees. So OH bond bond angle is 104.5 degrees. So this is called bond angles. Next, bond order. It is the number of bonds present between two atoms in a molecule. Bond order is number of bonds. For example, single bond, double bond. So in diatomic molecules, you have hydrogen, chlorine, fluorine, etc. The two atoms are held together by single covalent bond. As you already know, hydrogen exists as HH. Hydrogen, single bond, hydrogen. Similarly, chlorine exists as chlorine, single bond, chlorine, and fluorine also. The atoms are held together by single covalent bond. So the bond order of such bonds is equal to 1. So the bond orders of such bonds is equal to 1. Similarly, in oxygen molecule, O double bond O. We have O double bond O. And in nitrogen, N triple bond N. So nitrogen we have N triple bond N. So the bond order is 2 in case of oxygen, and in case of nitrogen it is 3. So the number of bonds. So what is bond order? Simple. It is the number of bonds present between two atoms in a molecule is called its bond order. Single covalent bond means bond order is equal to 1. Double covalent bond means bond order is equal to 2. Triple covalent bond is bond order is equal to 3. I hope it is clear. So this is called bond orders. So next we have bond energy. What is bond energy? It is energy. It is the amount of energy required to break 1 mole of bonds, 1 mole of bonds of a particular type between two atoms in a gaseous state. Means, for example, if you want to break the bonds between hydrogen and hydrogen bond, suppose hydrogen molecules should be changed into hydrogen atoms, gaseous state. So we require to give how much energy? 435.8 kilojoules per mole. 435. And hydrogen is existing in the form of single covalent bond. So how much of energy we have to give? If you give for hydrogen gas molecule 435.8 kilojoules per mole, then it breaks up into two hydrogen atoms, gaseous atoms. So this is called bond energy. Simple it is the amount of energy required to break 1 mole of bonds of particular type between two atoms in gaseous state. This is called as bond energy. I hope it is clear. Bond energy. Next. Similarly, for oxygen molecule, the double bond between two oxygen atoms is broken to form gaseous oxygen atoms. So it is requiring 498 kilojoules per mole. So if you give for oxygen molecule 498 kilojoules per mole of energy for oxygen molecule, it gets breaks up into two oxygen gas atom. So this is called bond enthalpy or bond energy. So bond enthalpy is 498 kilojoules per mole, and nitrogen bond enthalpy is 946 kilojoules per mole. So to split nitrogen molecule to nitrogen atoms, they require 946 kilojoules per mole. So by this, what you can understand here, the bond energy in polyatomic molecules, polyatomic means more than two or three atoms, more than three atoms or more than two atoms. We'll say it is polyatomic molecules. It is calculated by taking average bond energy of all the bonds. And here, very important point, as the number of bonds increases, for example, in case of hydrogen, it is single covalent bond. So as the number of bond increases, bond energy increases. I'm writing here the statement, as the number of bonds increases, bond enthalpy also increases. Also increases. This statement is very important. All of you, please make a note of this. So, as the number of bonds increase, bond enthalpy. How? Because in case of single covalent bond between hydrogen and hydrogen, we have it is around 435. Now it is 498 double bond, and triple bond it is more than the 946. So, by this, what you can understand, as the number of bonds increase, bond enthalpy increases. So, this is called a bond energy or bond enthalpy. Next, very important point, in water, there are two OH bonds, and these two OH bonds are not similar. As we know, the structure of water, it is represented by two OH bonds, and these two OH bonds are not similar. So the OH bond energies are not similar. One OH bond energy is 502 kilojoules, it is observed, and one another OH bond energy is 427 kilojoules per mole. So the average bond energy of higher OH bond is given by adding these two by two, means by average taking average 464.5. And very important, this is most important. All of you please can note this order they'll ask. So what is the bond energy order in halogens is chlorine greater than bromine greater than fluorine greater than iodine. This order is very important. So chlorine greater than bromine greater than fluorine greater than iodine means it is not following regular trend. The orders which you will not follow regular trend. Regular trend means what? Fluorine greater than chlorine greater than bromine greater than iodine or less than. They should follow like fluorine, chlorine, bromine, iodine, like in case of halogens. But they are following here chlorine greater than bromine greater than fluorine greater than iodine. So this bond enthalpy in halogens order is very important. So please make a note because they have asked this question so many times. Which are the following represents correct bond energy order for halogens? Correct bond energy order for halogens. So this type of questions are important. I hope it is clear now. Next we are going to have resonance. What is resonance? Some molecules are often represented by more than one Lewis structure. So certain molecules, if you see, they will have not one structure, they will have more than one Lewis dot structure. So the molecule cannot be represented by a single Lewis structure, which agrees with the experimental bond parameters. Such molecule is said to exhibit resonance. So in simple words, if you see, if a molecule has more than one structure, or if one structure is if for one molecule, if one Lewis dot structure is not explaining all its property, it will have more than one structure. Such type of molecules are said to be nothing but they exhibit resonance. Resonance is a phenomenon in which a molecule is represented by more than one Lewis dot structure. Very important. So the molecules which are exhibiting resonance, they will have not a single structure, they will have more than one Lewis structure, which differs only with respect to position of electrons. Why this structure is differing like this? Because of the position of electrons. Because of the position of electrons, the same molecule can represent in two or three ways. So that molecule is exhibiting resonance, but not with respect to atomic nuclei. So this is called resonance. The properties of resonance is very important for examination point of view. So the last statement based question, which of the following is incorrect about resonance, or which of the following is correct about resonance. So the different Lewis structures are known as resonating structures or canonical structures or contributing structures. The actual molecule is the hybrid. Hybrid means the total combination of all these. That is hybrid of all the contributing structures. Example, if you see ozone molecule. So ozone can be best represented in two ways mainly. So O single bond O and on one side it is double bond O. And here the same double bond we can shift this side and single bond this side. And if you see the picometers, that is O single bond O is 148 picometers and O double bond O is 121 picometers. Here just we have changed it. So ozone can be best represented in two ways. And the resultant ozone structure is this, that is called resonance hybrid, where we have single covalent bond both sides and average bond energy will be taking average bond and 128 picometers, 128 picometers. So this is called the resonating structure of ozone. So this is called the resonating hybrid of ozone. I hope it is clear. So this is nothing but resonance topic and resonance structures. Next we have in two contributing structures, the bond between oxygen atoms are 148 picometers and 121 picometers. In two contributing structures, the bond between oxygen atoms are 148 and 121. But the experimental value of over bond length of ozone is equal to each other and equal to 128 picometers. So this is experimental data. Actually, if you see separately, Over bond length in single covalent bond it is 148 picometers and double covalent bond it is 121 picometers. But actual experimental data it is equal to 128 picometers. Both sides it is equal. Thus the double bond is the ozone intermediate. Thus the bond length in ozone is intermediate between single and double bond length. Thus the contributing structures cannot explain this, and hence the ozone molecule exists as hybrid as shown in the figure. So actual ozone molecule means hybrid structure, that only 128 picometers of OO single bond and dotted lines we have to keep as in the previous slide we have seen. So that is called resonance structure. What are the properties of resonance or features of resonance? The resonating molecule cannot be represented by single Lewis structure. Already we know if a molecule is having more than one Lewis structure, then we can say that molecule is exhibiting resonance. That why it is exhibiting more than one? Because due to the position of electrons. That is what the resonating structures should differ only in position of electrons only, and the number of bond pairs and lone pairs should be same in all resonating structures. So third point is important. That is what the number of bond pairs and lone pairs of the number of bond pairs and lone pairs should be same in all canonical structures or resonating structures. So this is most important. I hope this is clear. Now let us see what are the other properties of resonance. The resonating structures have no physical existence. The molecules always exist in the form of resonance hybrid only. The molecule always exists in the form of resonance hybrid. Resonance brings stability for the molecule. Resonance brings only stability for the molecule. Means if it contains more number of resonant structures, again I'm writing here the statement, you can just see clearly. More the number of resonating structures, more stable is the molecule. More stable is the molecule. So more the number of resonating structures, more is the stability. So for example, based on this, they can ask in competitive exams this statement. They'll give three, four structures, three, four compounds, which are the following is most stable. So for example, if compound one is having two resonating structures, compound two is having three. So in between compound one and compound two is having more stability than compound one, because as the number of resonating structure increases, the stability also increases. So we have to see how many resonating structures it has. For example, in between benzene and toluene. Benzene, what is the formula? Benzene is C6H6. The structure will of benzene will be like this. Alternate double bonds. So for benzene, we can represent the benzene by shifting alternate double bonds like this. So here I'm keeping alternate double bonds. So this is also similar, this is also similar. So it has two resonating structures. Suppose if we take toluene, it has more than two resonating structures. So in between benzene and toluene, which is having more stability, toluene means methyl group on benzene ring. So in between benzene and toluene is more stable because it has three resonating structures. How many resonating? Three resonating structures. Whereas for benzene, we have only two, one and two. So as the number of resonating structure increases, stability also increases. Next, what is resonance energy? Resonance energy is defined as the difference in the energy of the resonance hybrid and the most stable contributing structure of the molecule. The resonance energy is always negative, indicating that hybrid is almost stable than the any of the contributing structures. So always resonance hybrid is more stable because its energy is always negative. So resonance energy is defined as the in ozone molecule, I have seen two structures of ozone and finally one structure of ozone, that is hybrid resonance. So that resonance energy is defined as the difference in the energy of the resonance hybrid and the most stable contributing structure of the molecule. So the resonance energy is always negative, indicating that the hybrid is more stable than any of the contributing structures. So that is called resonance energy. Next, so by this you can understand, you can click. So this is clear now. Next, we have other parameters, that is bond parameters is over. Next we'll see next topic in this. So next topic in this, I'm sharing the slides to the screen. Please watch it clearly. So next topic we have in this chapter, polar covalent bond. Very, very important. Simple it is. What is a polar covalent bond? When a covalent bond is formed between two similar atoms, then the electron pair is equally shared by two bonded atoms. Such a covalent bond is called pure covalent bond. But what is polar covalent bond? When a covalent bond is formed between two dissimilar atoms, identify this clearly. Just I'm underlining the important points. Two dissimilar atoms, the electron pair is unequally shared between two atoms. Why? Because the atom with higher electronegativity will attract the shared pair of electrons towards itself. Thus, the atom with higher electronegativity gets partial negative charge, and the atom with lesser negativity, electronegativity, gets partial positive charge. Such covalent bond is known as polar covalent bond. So, let us see examples of polar covalent bond. So one atom will be having higher electronegativity and the other atom. There are two dissimilar atoms and the other atom will be less electronegativity. So let us see the example HF. Now HF, if you see here, so HF, very, very important, HF or HCl. Any one example I'm explaining here, clearly you can understand. So hydrogen fluoride, if you take into consideration hydrogen fluoride. So here hydrogen fluoride. So hydrogen shares one electron, fluorine shares one electron. Due to more electronegativity of fluorine, already we know fluorine is having highest electronegativity. Fluorine is having highest electronegativity, and we know that fluorine is most electronegative. So it will pull the electron from hydrogen because hydrogen shares one electron. Here I'm writing again. Hydrogen shares one electron, fluorine shares one electron. But due to electronegativity of high electronegativity of fluorine, it will pull the electrons towards itself. Due to which what happens, hydrogen develops partial positive charge and fluorine develops partial negative charge. Partial means like this delta. So I'm writing here again, clearly if you can understand. So it is called partial positive charge delta and partial negative charge flowing. So due to this, what happens? Hydrogen lose its electron. The one which is losing the electron is called partial positive charge, and the one which is gaining electron, partial negative charge. So this is nothing but development of partial charges takes place on bonded atoms. Same thing happens in HCl as well as ammonia also. Nitrogen is more electronegative than hydrogen. So the electrons will be lost by hydrogen and they will be pulled by nitrogen. So this type of unequal sharing of electrons between two electron atoms, between two different atoms with different electronegativity, it is nothing but polar covalent bond. I hope it is clear. And due to the development of partial charges, the molecule is said to be very, very important. The molecule is said to be a dipole and it possesses a dipole moment. So this is called dipole. And the symbol for dipole is nothing but since electrons are flowing from hydrogen towards fluorine, so it is nothing but the symbol for dipole. This is called dipole. So there exists a dipole between dipole moment. So this is called dipole. Due to the development of partial charges, the molecule is said to be a dipole. Dipole means one partial positive, one partial negative. That is called dipole, and it possesses a dipole movement of electrons. So this is very, very important. Now we are going to discuss more about dipole moment. So because polar covalent bond, it is there in school level also, but in this concept, in this 11th class, we are going to discuss more about not polar covalent bond. We are going to discuss about dipole moment. I hope it is clear now. So let us see what is dipole moment. It is dipole moment is the product of magnitude of the charge. Product of magnitude of the charge, that is partial positive and partial negative, and the distance between the two charges, that is the distance between partial positive charge and partial negative charge. So dipole moment is determined by the Greek letter alphabet. It is mu. So mu is equal to dipole moment is equal to q into d, where q is called charge, that is partial positive and partial negative, and d is called distance. So dipole moment is expressed in dBs. 1 dB is equal to 1 dB of essence is equal to 1 in 10 to the power minus 18 ESU, and 1 dB is also equal to 3.3356 10 to the power minus 30 coulomb meter. So where C is called coulomb, M is called meter. So this is the basic unit, CGS unit, and this is the SI unit. and 1 dpi is equal to 1 dpi is nothing but 1 in 10 to the power of minus 18 ESU. So the problems related to dipole moment is also important. We are going to discuss that in the coming sessions. So what is dipole moment? Basically, it is the product of magnitude of the charge and the distance between the two charges. Dipole moment is represented by Greek alphabet. Mu is equal to Q into D. I hope it is clear. Next. So dipole moment is a vector quantity because it has direction and it is represented by an arrow pointing towards the negative end of the dipole. The dipole moment of HF is represented as H single bond F. So as the electron is pointing towards flow in, we'll say dipole, the arrow mark is pointed towards the direction of electrons, direction of electrons. So this is called dipole moment symbol. So I'm writing here the symbol of dipole moment. You can easily understand this is the symbol of dipole moment. It means that electrons are transferring from hydrogen to fluorine. Suppose if the arrow mark is facing towards hydrogen, we can say electrons are flowing from fluorine to hydrogen, but it is not possible because fluorine is more electronegative and hydrogen is less electronegative. So this is called dipole moment. So dipole moment is very, very important. What is dipole moment? Dipole moment is a vector quantity and it is represented by an arrow pointing towards negative end of the dipole. The dipole moment of HF is represented as like this. Next. So dipole moment a vector quantity continued. So the arrow mark indicates, as I told you, the arrow mark indicates the direction of shift of electron density in the molecule. In HF, fluorine being more electronegative attracts the shared pair electron towards itself. Hence, the shared electrons are shifted towards fluorine atom. In polyatomic molecule, each of the polar bonds represented in the polyatom is more than 2. So in polyatomic molecules, each of the polar bonds represent the molecule contributes towards the dipole moment of the molecule. So the net dipole moment is the resultant of individual bond moments. Net dipole moment is the resultant of individual bond moments. For example, let us see in water molecule we'll have two OH bonds and OH bonds are polar bonds and the net dipole moment because oxygen is more electronegative than hydrogen. So oxygen will pull the electrons towards itself. So oxygen will pull the electrons, shared pair of electrons from hydrogen. So that's why the dipole moment symbol like this and the resultant dipole moment will go like this. So the net dipole moment of water is the resultant vectorial addition of two bond moments. So vectorial addition of this bond moment and this bond moment and here this is called the resultant dipole moment. So this can be represented in the diagram as shown in figure. So this is called dipole moment. I hope it is clear. So dipole moment means nothing but the migration of electrons towards the most electronegative atom. That is from one atom which is having less electronegative to the other atom which is having more electronegative in a molecule. It is nothing but dipole moment and it is defined as the product of Q into D, that is charge into distance. In some molecules, the individual bond moments get cancelled to have a zero dipole moment. For example, BCl3, boron trichloride. BCl3 is nothing but what? Boron trichloride. This instead of this, I'll give you one more example, simple example. So if we take into consideration CCl4, CCl4, one chlorine, second chlorine, third chlorine, and fourth chlorine. This is called CCl4 molecule. I'll say the resultant dipole moment of this molecule is zero. Why? Because so here the electrons are going from carbon to chlorine because chlorine is more electronegative. So the electrons are going from carbon to chlorine from all the sides. The electrons are going from carbon to chlorine. That's why I'm changing the arrow marks. So this is opposite pull, opposite pull. So these two will cancel out each other. These two will cancel out each other. Due to opposite pull, they cancel out the four times. So hence the net dipole moment mu is equal to zero for this molecule because they have mutually cancelled. Because this is pulling the electron toward this side, this is pulling the electron toward this side, this is pulling, and this is pulling. So opposite moments cancel out each other. So this is nothing but what dipole moment. I hope it is clear. Let us take into consideration BCl3. Also, you observe the same thing. So in BCl3, electrons are going from B to Cl. So all the three sides. So it will be going like this. So vector addition, vector products. So you'll get net dipole moment is zero. So it is following vectors. So those who have taken max background, they can understand vectors. But to our knowledge, simple, we can have to remember that addition of vectors mutually gets cancelled. Next. What is polarization? Next property we have. What is polarization? Covalent molecules possess ionic character due to the development of partial charges. As we already seen, polar covalent molecules, in which the sharing is unequal. They develop partial positive charge as well as partial negative charge. So these covalent molecules possess ionic character due to the development of partial charges. Very similar to covalent compounds. Even ionic compounds possess covalent characters also. So this partial covalent character of ionic compounds is explained by Fuzzen's rule. Very, very important. Based on Fuzzen's rules, you'll get one definitely one objective question. So what is Fuzzen's rule? We'll discuss. So what are Fuzzen's rules? The partial covalent character of ionic compounds is explained by Fuzzen's rules. Now we'll see what are Fuzzen's rules. Very easy to understand, but there is logic in this. So try to understand the logic first. So when a cation approaches the anion, see here, what is polarization? I'm explaining you clearly. When a cation approaches the anion, the electron cloud of anion is attracted by cation because cation is positive charge and the anion is negative. So automatically they have unlike charges attract each other. And the electron cloud of anion is distorted. Very, very important. Distorted means disturbed. So this type of distortion of electron cloud is known as polarization, and that this distortion results in the increase of electron density between two nuclei because electrons are attracting the cations. As a result, the ionic bond acquires a covalent character. So some atoms of ions also, some ionic compounds also will have covalent characters. So based on this concept only, and the concept is polarization. What is polarization? When a cation approaches the anion, the cation is attracted by the anion, where the anion electron cloud gets distorted. This type of distortion is known as polarization. Let us continue. The ability of a cation to distort the electron cloud of anion is called polarizing power. The ability of anion to get distorted is known as polarizability. As the size of cation decreases, the polarizing power also increases. Very, very important for objective. So this characters only important. As the size of cation decreases, the polarizing power increases. Means small cation will have high polarizing power and large anion will have more polarizability. So small cation and large anion will have covalent character. For example, if we take into consideration, let us consider lithium iodide. Lithium is small cation and iodine is large anion. They form a compound called lithium iodide. So lithium iodide is not ionic, it is covalent in nature. So we have some metals and non-metals which are covalent in metal and non-metal combination which are covalent in nature. That is based on polarizing power. So what is the polarizing power? The ability of cation to distort the electron cloud of anion is known as polarizing power. Small cation will have more polarizing power. As the size of cations decreases, the polarizing power increases, and size of anion increases, the polarizability increases. So due to which covalent character also develops. So lithium iodide is covalent. Lithium iodide is covalent than lithium fluoride. Lithium fluoride is ionic because small cation, small anion. But lithium iodide small cation, large anion. So lithium iodide is covalent, whereas lithium fluoride is ionic. It is ionic. So this is called polarizing characters. So I hope it is clear. Next, Poisson's rules. Smaller the first rule is what? Smaller the size of cation. From this Poisson's rules, you'll get one question in the objective. So what is Poisson's rule? First one, smaller the size of cation, higher will be its polarizing power, and greater the size of anion, greater will be its polarizability. Hence, an ionic compound containing small cation and large anion will have greater covalent character than ionic character. Example, lithium iodide. Lithium iodide, small cation, large anion. I hope it is clear. This is first rule of Poisson's rule. Next. So out of HH and ClCl bond, which one has higher bond energy and why? See, already I told you single covalent bond and single covalent bond, but this is hydrogen with less atomic number and chlorine with higher atomic number. Since the size of atom decreases, as the hydrogen atom is very small when compared to chlorine, so hydrogen molecule is very, very small. So they are very close to each other. As they are close to each other, we require more energy to break that bond. As these two are far each other because the atomic number of chlorine is 17 and that of one more chlorine is also 17. So answer is HH bond. I hope it is clear. Next example two. Out of oxygen molecules and nitrogen molecules, which one has greater bond energy? As I already told you, as the number of bonds increases, as the Number of bonds increases, bond energy increases. As the number of bonds increases between two similar atoms is important, bond energy also increases. So answer is nitrogen. So triple bond. Because oxygen contains sorry, oxygen is O double bond O and nitrogen is N triple bond N. Already we know this. Next, example 3. CC bond length is in ethane is 154 picometers. Ethane is alkane. Ethane is what? Alkane. So ethane is alkane. Its formula is C2H6 in which carbon and carbon are linked by single covalent bond. Whereas ethylene is alkyne. Ethylene is alkene. Alkene. Ethylene is alkene where they have carbon carbon are linked by double covalent bonds. Since double covalent bond is having less bond length when compared to single covalent bond. So because bond energy is more and bond energy is less in this case. So this is nothing but answer is CC bond length is more. This is due to bond length is less for single covalent bond when compared to double covalent. In ethylene, two carbon atoms are held together by sigma bond and a pi bond. While ethane, they are held by only sigma bond. What is sigma bond and pi bond? We'll discuss later because that topic has not yet come. But to my knowledge, here single bond is there. Single bond means it has one sigma bond. Double bond means one sigma, one pi bond, and that's why it is more. Next, and the following species in order of decreasing bond angles around the central atom in each set. Decreasing bond angles. So this is CH4, it is an alkane. And so first one is what? CH4. CH4 is an alkane. Ammonia, water, BCl3, C2H2. Simple it is. As the number of lone pairs increases, bond angle increases, decreases. So I'm writing here the statement. As the number of lone pairs, very, very important, lone pairs increases, bond angles decreases. Simple it is. So in CH4 there is no lone pair, zero lone pairs. It has one lone pair, it has two lone pairs, and it has electron deficient compound, less electron deficient, and this is having triple bond C, triple bond C because C2H2. So decreasing bond angles. So here ethane is having 109 degrees, methane, sorry, it is 107 approximately, and water already we know 104.5, and BCl3 it is less than 104.5, C2H2 is 180 degrees because it is linear shape. So as the number of bonds increases, bond angles increases. As the number of bonds increases, I'm writing here, as the number of bonds increases, as the number of bonds increases, bond angles increases. As the number of bonds increases, bond angles increases. In case of ammonia, ammonium ion also the same. So answer is first one. First is highest. So this is BCl3. Next is methane. Next ammonia. Next water. Final BCl3. So I hope it is clear now. So I'm clearing the page. So you can see the answers. I think this is over now. So next concept we have. Next concept in this chapter we have very important concept. More about dipole moment we are going to discuss now. So more about dipole moment we are going to discuss. So the dipole moment we are going to discuss now in these slides. So let us see now. Coordinate covalent bond. This is a special type of covalent bond in which the shared electron pair. So we have polar covalent bonds, non-polar covalent bonds, coordinate covalent bond. This is a special type of covalent bond in which the shared electron pair is contributed by one of the bond atom only. Shared electron is contributed by one of the bond atom only, and it is also known as dative bond. Dative bond. So the atom which donates the electron pair is known as donor, and the atom which accepts the pair of electrons is known as acceptor atom. So formation of ammonia boron trifluoride, and the donor atom gets a formal positive charge, and the acceptor atom gets a formal negative charge. During dative bond formation, the hybridization of the atom may change. So, what is dative bond? Formation of ammonia boron trifluoride. And in coadative bonds, we have one molecule or one species should have at least one lone pair of electrons, and the other molecule should be having electron deficient. So it should accept readily that electron deficient compound. So these two species together they form ammonia boron trifluoride. So together they form ammonia boron trifluoride, and here ammonia is called donor because it is donating lone pair of electrons, and BF is called acceptor. So this is called acceptor, and ammonia is called donor. And on the whole, the bond is called dative bond or coordinate covalent bond. So a dative bond is formed between two atoms in which one of the atoms should have lone pair. First condition, they should have at least two atoms in which one of the atoms should have a lone pair of electrons and the other atom should have empty orbital and should be electron deficient. As I told you, boron trifluoride BF3, it is electron deficient. So electron deficient means after sharing, as it discussed in the previous class, what are electron deficient compounds? After sharing, they are getting less than 8 electrons in the valence shell. So that is nothing but electron deficient. Like in the case of BF3. BF3, after sharing, it has only 6 electrons in the valence shell because boron is having 3 electrons in the valence shell, and these 3 electrons are shared by 3 fluorines. So on the whole, after sharing, it is getting only 6 electrons. So it is incomplete octet, which are called as which are called as which are called as they are called as electron deficient. I hope this is clear. Formation of ammonium in example, the lone pair of nitrogen, because nitrogen is having 3 electrons, 5 electrons in the valence shell, and it is donated to a proton to form a dative bond between nitrogen and hydrogen. The nitrogen gets a formal positive charge because of 5 electrons. So I hope it is clear. This is called coordinate covalent bond, and so also called as dative bond. So nitrogen is having 3 electrons it shares and 2 more electrons it has in, it is getting 2 proton. Proton is nothing but H plus, and finally forming one hydrogen will share 1 electron and proton will take 1 electron. So due to which what happens, it forms NH4 plus. NH4 plus. So NH4 plus formation is very, very important. I hope it is clear. So this is called, here nitrogen is called donor and hydrogen is called acceptor. The proton is called acceptor, not hydrogen. We can say proton is acceptor because it is accepting 2 electrons. So I hope it is clear. Next, combination of aluminum chloride and ammonia. Aluminum chloride is a AlCl3 is an electron deficient compounds. So already I told you what are electron deficient. After sharing, they are getting only incomplete octet. So that's why they are called as electron deficient compounds. The aluminum atom requires 2 more electrons to complete the octet. Hence, the lone pair of electrons on nitrogen is donated to aluminum atom to form a coordinate covalent bond. The aluminum gets a formal negative charge as it is accepting the electrons, and nitrogen gets a formal positive charge as it is gaining and donating the electrons. So the hybridization of aluminum changes from sp2 to sp3. So this hybridization topic we will not discuss here because it is being separated. So this is called coordinate covalent bond. So combination of aluminum chloride and ammonia diagram is there clearly. So nitrogen is having one lone pair. It is donating to aluminium. So nitrogen is donating, so it is getting plus, and aluminum is accepting, it is getting minus. So by this we can say total compound is stable. Covalent compound. Now we'll see discuss what are properties of covalent compounds. As covalent compounds can exist in solids or liquids or gas at room temperature. They have relatively lower boiling points. Just recap of this concept. Complete covalent compounds. So they have relatively lower boiling points than ionic compounds. They are poor conductors of heat and electricity. In general, the covalent compounds are soluble in water but soluble in non-polar solvents. The covalent bonds are directional in space, hence they possess regular three-dimensional structures. These compounds show isomerism, which are nothing but in organic chemistry we'll discuss. So the covalent compounds are directional in space. Already we discussed this, that's why I'm not discussing more. Now, what is polar covalent bond? Dipole moment already we discussed. So it is mu is equal to E into D, and 1 d by is equal to 1 in 10 to the power of minus 8 in the SU. It is in coulombs. Meter means 3.33 in 10 to the power of minus 30. Nothing but the dipole moment is the product of charge and magnitude of the charge. So magnitude of the charge. So the bond moments and vector quantities and the resultant vector of all the bond moments will give the net dipole moment of polyatomic molecules. So in case of polyatoms, the dipole moment can be zero. So let us consider two bond moments A, B, and AC inclined at an angle of theta. The resulting bond moment is given by the formula mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. Anyway, the application of this formula is not important. So if theta is equal to 0, mu r is equal to mu1 plus mu2, the resultant will be maximum. If theta is equal to 180 degrees, then the resultant will be minimum because it is equal to mu r minus mu r is equal to mu resultant is equal to, that is dipole moment. Resultant dipole moment is equal to mu1 minus mu2. So example like this. So mu1 plus mu2 or mu1 minus mu2. It depends upon theta values. Very, very important. Next, applications of dipole moment. We can calculate the percentage of ionic character. Very, very important here. We can calculate the percentage of ionic character in a covalent molecule. That is the main application. So by using dipole moment, the value of dipole moment can be used to calculate the percentage of ionic character in a molecule. Assuming the bond to be completely ionic, the theoretical dipole moment is being calculated. So mu theoretical is equal to 1.602 10 to the power minus 90, that is charge of electron into bond length, which is present in meters. So you'll get the mu theoretical value in dBys. So how to calculate percentage of ionic character? We'll see if possible one problem is there. Then definitely I'll explain that problem. You can easily understand. So calculation percentage of ionic character is equal to mu experimental by mu theoretical into 100. How to calculate mu? Q into D. Q into D. And mu experimental is dipole moment. Where using electronegativity values also, we can find out percentage of ionic character. That is percentage of ionic character is equal to 16 into electronegativity of A minus electronegativity of B plus 3.5 into electronegativity of A minus electronegativity of B whole square. So these are the thing about electronegativity values of A and B respectively. So these two formulas are most important. We'll discuss numericals on this if possible. So determination of geometry of the molecule. So the value of dipole moments of molecule indicates the geometry of them. Molecules like CO2, CS2 has zero dipole moment. How it is zero dipole moment we are discussing now. So molecules of CO2 and CS2 have zero dipole moment because opposite they'll pull each other, and it shows that these molecules are linear in shape. Water has permanent dipole moment, which indicates that water is not linear molecule and has a bent shape. So with the dipole moments, you can find the shapes of molecules. Also in ammonia, the three hydrogen atoms are not symmetrically around nitrogen, and it has a dipole moment because the electrons from hydrogen will go to nitrogen because nitrogen is more electronegative than hydrogen. So ammonia has a pyramidal shape. So with the moment, by the means of dipole moment, we can know the shapes of molecules. I hope it is clear. So how to calculate dipole moment also we discuss. To distinguish, very important point. This discussion we are discussing organic chemistry, but here it is there. So that's why we are discussing now because dipole moment is there for organic as well as inorganic compounds. So to distinguish between cis and trans isomers, cis means similar groups are present on the same side of a alkene, and if similar groups are present on the opposite sides of an alkene, we can say it is called trans isomerism. And organic compounds can show geometrical isomerism. The cis and trans isomers have different dipole moments. The values of dipole moment of these isomers help us to distinguish between cis and transforms. Generally, the transform is symmetrical and has zero dipole moment because opposite, and cis form will have permanent dipole moment. So cis is having more dipole moment than trans. Very important. Cis is having isomers are having more dipole moment than trans isomers. Trans isomers have zero dipole moment. So for example, cis isomer of 1 comma 2 dichloroethene. It is called what? 1 comma 2 dichloroethene. Cis means similar groups are present on the same side. Trans means similar groups are present on the opposite side. You can see here. So here chlorine is presenting on the same side. Similar groups are present on the same side. And here chlorine is present on the opposite side. So there exists dipole moment for this. For the trans isomer, what happens? They cancel out each other because the electrons are flowing towards carbon to chlorine and for this carbon to chlorine. So these two isomers are equal and these two dipole moments are equal and opposite. They cancel out each other. So whereas this, they'll go from this side and they'll go from this side. So upward moment, downward moment. So they are not opposite each other. They cannot cancel out. For cis isomers, maximum dipole moment, and for trans isomer, zero dipole moment. I hope why it is zero. You can understand. You understood it clearly. Next. To determine the orientation of groups in benzene ring, very important. Third and fourth points are most important for dipole moment. For cis and trans isomers which are having more dipole moments, cis. And to determine orientation of groups in benzene ring, the values of dipole moment are useful in predicting the orientation of groups in benzene ring. In benzene ring, we have three types. One is orthoisomer, meta-isomer, and para-isomer. So out of this, which is having more dipole moment, let us see. In isomers of dichlorobenzene, the dipole moments are as shown below, now. So chlorine and chlorine. This is called orthoisomer because chlorine is present at O position. This is called what? Ortho position. So O isomer, M isomer, and P isomer. Ortho, meta, and para. So P is O M P. So P for P isomer, mu is equal to 0, and highest is for ortho. Next is meta. So our order is O greater than M greater than P. As an exception, some of the para isomers possess a permanent dipole moment. So they have permanent dipole moment. This is the exception. So these two. So in between ortho, meta, and para of same compound, same molecule. So we have ortho is greater than meta is greater than para positions. I hope it is clear. Next. So in this class we discussed about dipole moments. So all the dipole moments are important. And by this we are ending this session. And this class is most important. I hope it is clear. So lecture 3 is completed. Next we'll see lecture 4 different topics. So thank you all. Have a nice day.